Okay. So at present I am going to continue with part 2 of the lecture of 29th of November 2016. Alright, so I was at the point of calculating the ratio of two complex numbers. So let's continue that. And furthermore, after finishing off something here, I will need to go back and correct a problem that I did from chapter 4. Okay. So to finish this question off, so we multiply by the conjugate. This is called, maybe I didn't say that before, but this is called the complex conjugate of this number. So a plus bi, for any complex number, the complex conjugate is a minus bi. Okay, and then, so continuing this calculation, we have 1 plus 2i, and then 3 minus 4i, divided by, now we can do this calculation, multiply, and we get 3 squared plus 4 squared. Okay, so for such a complex number and its complex conjugate, the result will always be, when you multiply them together, the sum of two squares, the square of the real part plus the square of the imaginary part. So here we get 9 plus 16, which is 25. And in the numerator, we'll get 3. Just finding the real part, we have to take this times this is 3, and this times this is minus 8 times I squared, which is plus 8. And then taking the other two terms, we get minus 4 plus 6, which is plus 2i. And so altogether we get 11 plus 2i over 25. Or if you multiply, you can divide each number by the distributive law, each term in the numerator by 25. You can divide each term in the numerator by 25 just by using the distributive law. All right. And I wanted to be thorough here and check for you, in case you did a calculation you wanted to check this. The easy way is simply multiply by 3 plus 4i. So we multiply this by 3 plus 4i, and that should give us, in the end, 1 plus 2i. So if it doesn't, then we've made a mistake somewhere. So 3 plus 4i times this gives us, well, I can take the 25 outside, leave it in the denominator, and multiply the two factors in the numerator, 3 plus 4i and 11 plus 2i. What I get is 3 times 11 is 33, minus 8, 33 minus 8 is 25, and then 3 times 2 is 6, plus 4 times 11 is 44, 6 plus 44 is 50i. And if I divide by 25, I can see I'm going to get 1 plus 2i, which is correct. Okay, so that's our check. All right. Okay, before I continue, as I said, I made a mistake in doing problem number 20 in part 1, and so I will just go back and review that. Let me just check the sound here, make sure it's all okay. In part 1. Yeah, okay. Good. All right, so this was chapter 4, practice test. Number 20. Okay, so remember we had a triangle which was given by y is equal to 12 minus 4x. So it was a line, is a triangle bounded by the sides, the y-axis, okay, so we had 1, 2, 3, so this was 3, 6, 9, 12. Then we had 3 here, using the same scale, and this line here is part of the triangle. So this line here was part of the triangle, this line was part of the, was another side of the triangle. Try to make it straight. But the third side I got wrong. I was saying that it was going through the point 3, 0. But the book actually says that it's the line that is perpendicular to this line, which they called f. So f of x is equal to this, so they just called it f, that line. The other line, g, is perpendicular to that line, but it's going through the origin, not through this point. Okay, so the graph looks like this. So this is the line G. I'll put a dotted line when it's outside of the triangle. G. Okay, so on the one hand, this will make it easier to find the equation of the line G, because we know it's going through the origin. But on the other hand, these side lengths are, it becomes a little bit more difficult to calculate the area of the triangle. Okay, so anyway, apologies for putting you through that whole calculation with the wrong line. Anyway, that could be the answer to another problem, which is not unfortunately this one. So obviously you would have tried to be working on this one. So the line that goes through the origin and is perpendicular to f will be of this form. Okay, since it goes through the origin, the y-intercept is going to be 0. So we'll just write that as an arrow with a 0. That just becomes 0. And the slope is the same slope as I had before, namely 1 over 4. Okay. Okay, so now the next step is, in order to find this length L1 and this length L2, I need to find this point. I need to find the coordinates of this point. Okay, so my two equations, I have to solve my two equations for both x and y. All right? So I've solved this system of equations in two variables, two equations and two unknowns. And that will give me the point of intersection. The x and y coordinates will be the point, will give me will be the coordinates of the point of intersection of the two lines. Okay, so this again should be a bit of a review. You can do it by, we'll do it by substitution. So we can substitute y equals 1/4 x on this side of the other equation, right? And then you get this equation, and we simply solve for x. So 4 goes on this side. 4 plus 1/4 is the new coefficient of x, and that's equal to 12. So 4 plus 1/4 is 16 plus 1, 17, all over 4. And so I solve for x, and I get x is equal to, multiply by 4 over 17. 4 times 12 is 48. 48 over 17. Okay. So it's a value that's just slightly less than 3. As you can see, 51 over 17 would be 3. So it's just slightly less than 3. That makes sense. And on the other side, the other coordinate, let's calculate that. Is y is equal to, and we can simply use this equation. So that's the simplest way to get y. And you can check it with this equation if you wish. It's always good to check. So 48 over 17, and then divide by 4. So the numerator gets divided by 4, and we get 12 over 17. You can't cancel between the numerator and this bigger denominator, right? This is equal to 48 over 17. So just remembering your fractions. Okay, so the coordinates of this point then are x is 48 over 17, y is 12 over 17. Now let's find L1. So, okay, L1 is the distance between this point 12, 0, 12, and this point 48 over 17, 12 over 17. So the distance between the 2 points is, using the Pythagoras theorem, it's the difference in x coordinates, 0 and 12 over 17 squared, and 0, that quantity squared, plus the difference in the y coordinates, which are 12 minus 12 over 17, quantity squared. Oh, sorry, the x coordinate is 48 over 17. (48 over 17 minus 0, quantity squared, and then 12 minus 17, 12 over 17, quantity squared. All right, now just doing this calculation, there's fortunately some simplification. So this is 48 squared over 17 squared. And this is I can take a factor of 12 outside, and I get 1 minus 16 over 17. Right? Sorry, 1 minus 1 over 17. And this whole thing will be squared. So I get 12 squared coming out, and this fraction will be 16 over 17. Okay, so I'll take this whole thing and square it, and I'll put the factors that I have here. I'll just square each of them. Okay, so that's what I get. Now what I'm going to do is I'm going to take the common factors out so I can more easily calculate this thing. So the common factors will be, there'll be a factor of 48 here if I put one of the 16 with the 12 squared. then I get a factor of 48 squared. Okay, so this is 48 squared times 4 squared. And everything's square root. So I take this common factor, 48 over 17, outside. And then I get square root of 1 plus, and what I'm left over here with is 4 squared. And this whole thing is 1 plus 16, which is 17. So the square root of 17 under the square root will cancel. There are actually two square root 17s here, so one will cancel with the one above in the numerator. And I'll get 48 over root 17, just to make the answer look as simple as possible. It will turn out the other L2 will also have a square root of 17 in the denominator, and in the end the square root will cancel away, and I'll get a rational number. Okay, let me just check that. Okay, yes. All right. Okay, the other thing to calculate is L2. What is the length L2? So again, I use the distance formula. And L2 is equal to the square root of the x-coordinate minus 0. The two coordinates are, the 2 points are 0, 0, and 48 over 17, 12 over 17. So I take the difference between the x-coordinates, square it, and the difference between the y-coordinates, and square that difference. And then take the sum of the differences and then the square root. All right, so what I get then is 48 squared over 17 squared. Okay, I have to keep the square root in here. 12 squared over 17 squared. Okay, so I take common factors out. I take the largest common factor out that I can, and that's going to be 12 squared over 17 squared. So first I take that common factor outside of the brackets here, within the square root. And then here I get, this will be 12 times 4, each number squared, right? So this is looking like that. And so we get 4 squared is the remaining factor from this one, and 1 is the remaining factor from this one. Again, I'll get 17 here. And so this whole thing becomes, in the end, 12 over root 17. Okay, you can now take, since there's the product only, 17 will cancel 7 with one of the 17s here, and that gives me root 17. And then this 12 will come out, 12 squared will come out, and I'll get 12. All right, so the end result, calculating the area, since these two lines are perpendicular, the area is simply L1, L2 over 2. And that gives me, this is L1, 48 over root 17, and then 12 over root 17. All over 2, and then I get cancellation here, right? And then 6 times 8 is 48, 4 times 6, 24, 288 over 17. Okay, so that's what I get for an answer to that problem. It's not, I admit, this was not an easy problem. However, using what you know about distance formula, correct construction, and just doing the algebra properly should give you this answer as correct. Okay. All right. Oh, and by the way, it's numerical value. It's just below 17. In fact, 16 and 16/17, which is 17 minus 1 over 17. So it has some strange form. I'm not sure why exactly this is the form, but that's what it comes out to be. Sort of a special, I don't know, symmetric form. Okay, so if there are any further questions on that problem or the others, then please let me know. Also, I checked the answer to, I believe it was the next problem, number 21. No, I think one of the problems had answers in the back of the book which were different from the answers that I gave, and I think that was because I think it was number 21. Let me just check that. Okay. No, that was 21. We did that. Answer was correct in the back. Oh, it was a graphing one, yeah. So the number 23, 24, 25. I think the points that they used were to find the line, to find the equation of the line. So 23 had no question in the book, so I couldn't really answer that. But 24 had the question, find the linear function y where y depends on x, and the number of years since 1980. So the 2 points you could use that I used were 5 and 16, measured in thousands. Y is measured in thousands of people. Sorry, thousands of dollars of this is profit. So I used these points, and the book used 32. The book I discovered apparently used the points 5 and 15,000. So the book didn't use the didn't make it easier by. I mean, it didn't measure it in thousands of dollars, but in actual dollars. Okay, so they took the point through the first year 5 to be 15,000, and the point through 25 was 32,500. Okay, so those were the two ordered pairs for that graph. Okay, so in the end, it looks like they got 875 plus. I had to record this here. 875x plus 10,625. Yeah. So, and you'll find that if you plug in x equals 5, you get 15,000, and if you plug in x equals 25, you get 32,500. So those were the points that were chosen. So in this case, the answer would vary depending on what actual numbers you chose here. So this was pretty close to what I chose for the second one, but for the first one, it was a bit more off. So So what I got, if I use my points, I got 800x plus 12,000. So they're a little bit off compared with this, but that's what I got, if you recall my answer. Okay, number 25. Find and interpret the y-intercept. So the y-intercept is the profit in the year 1980. So here it would have been $10,625, and this would be $12,000. So if you were to answer this, you would just pick points. You pick 2 points, and depending on what you got, you possibly could get a different answer. But in grading it, I would just check to make sure that the points you got were reasonably close, and that your answer was correct from those points chosen. Right? I chose different points, and I got that. All right. So here, there's no real one correct way. It depends on your original choice of the points from the graph. But it should be reasonably close to one of these 2 answers. And you just have to specify which units you made, so that means the definition of y and x as well, and to stick with those definitions. All right. Okay. So let's go back to complex numbers and their application to factorizing polynomials. So this is back in section 5.5 and so on. Okay. All right, so this was something, again, I stated this in the lecture on the 26th of November, but it didn't make it through. So I'm doing this lecture, redoing it. So roots of polynomials. Okay, so this is true now for any polynomial with complex coefficients. So we have a polynomial f of x is equal to an x to the n plus, so that's the leading order term, an is not equal to 0, plus an minus 1 x to the n minus 1, and so on. All the terms from the first one, possibly somewhere 0, but this one cannot be 0. All the way down to a1 x1 plus a0. Okay, so that's a general polynomial. an in general are the ai, where I is an index running from 1 to n minus, just n, starts from 0 actually, are complex numbers. Okay, so in general, any polynomial with complex of degree n, so the degree of f is n, and with complex coefficients has n complex roots. Possibly with multiplicities bigger than 1. But the sum of the multiplicities is always n. Okay, so this result is always true. Okay. Now there are always going to be, there might not be any real roots. Actually, there are cases where you don't have any real roots at all. But you could, the most number of real roots you can have is n. But you can essentially you can have the full number of roots, or it would be less by multiples of 2. Okay, so what the reason for that could be less than n by multiples of 2. So if n is equal to 3, for example, then you can either have 1 real root or 3 real roots. You can't have 2 real roots and nothing else. Unless you have a repeated root, actually. Yeah, so you could have a repeated root. That sort of counts as 3, because the multiplicity will be 3. Okay, but the point is that I was going to make was that if you have a complex root, so it has a non-zero imaginary part. The real part could be anything, but the imaginary part has to be non-zero. Then you'll also have the complex conjugate of that root will be also a root, but only if the coefficients of the polynomial are real. So we'll usually only consider this case. Usually only consider polynomials with real coefficients. Yeah. Okay. So this is a condition under which all those statements are true. Okay. This is always true for any complex coefficients, but in particular, if the coefficients are real, then if you get a complex root among all these n roots, then you have to have the complex conjugate as also a root. Okay. So, for example, in this case, x squared plus x, that was equal to x plus 1, x squared plus 1. And that factored into x minus I, x plus I. And so 2 of the roots are complex, namely xi and x equals minus I. And the other one is real. Right. Okay, so let's see why the roots come in complex conjugate pairs. So the roots of a polynomial complex roots of a polynomial always come in complex conjugate pairs. Okay, so here the complex conjugate of I is minus I. The complex conjugate just changes the sign of the imaginary part. It leaves the real part the same. So I goes to minus I, 0 goes to 0. That's the real part. Right? It's a pure imaginary number. Okay, so why is that? Okay, so let me go through the reasons why you have this to be true, why this is true. So if Z1 is one complex number, a plus bi, and Z2 is another complex number, c plus di, then I want to show you that if you take the complex conjugates and then multiply, then you get the same thing in the end, as you would if you first multiplied the complex numbers, z1 times z2, and then took the complex conjugate. Okay, so this is true. Why is it true? Let's see. So if I put in a minus bi, that's the complex conjugate of z1, and the c minus di, complex conjugate of z2, then what do I get? I get on this side ac. Now minus b times minus d is plus bd, but then I have an I squared, so it's minus, oops, that should be ac, should be minus bd. ac minus bd. And then I take the cross terms here, and I get ad minus ad minus bc. So the whole thing is minus ad plus bc, where I took the minus sign out of both terms outside the brackets, and then times I. Okay, on this side, what is my complex number z1 times z2? I multiply it and I get ac minus bd plus now ad plus bc times I. So this, the real part is the same as over here, but the imaginary part has changed by a sign. So this is equal to z1, z2, and then take the complex conjugate. Okay, furthermore, if I take the sum of two numbers and then take the complex conjugate, that's the same as first taking the complex conjugate and then taking the sum. Okay, so that's easier to prove than that. So I'll let you verify that on your own. Okay, so you could just use this formula and work through it in this kind of step. So verify one side and then the other. That okay, z1 plus z2 complex conjugate is equal to z1 plus z2. Okay, so just check that. All right, now suppose I have. So I want to put all this together. Also, if I multiply by z by a real number a, let's call it k. So k is real. And then I take the complex conjugate, then you can also verify that the k comes right outside, is unchanged, and z1 is conjugated. All right, k, it's because k conjugate for real, k is equal to k itself. Okay, I'm just using this property along with k conjugate is equal to k. All right, I'm using, this notation means complex conjugate, by the way. I should have mentioned that before. All right, so now if I take the polynomial f of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus all the way down to a1x plus a0. So that's my polynomial. Now suppose r is a root, and r is complex. So if x equals r is a root, then when I plug r into the equation, I get 0 for my polynomial. So I get the whole thing is equal to 0. Okay, now I take the conjugate of that whole thing. So the conjugate of 0 is just 0. If I take the conjugate of both sides, I leave the equation unchanged. But the conjugate of 0 is 0. Right? It's real, so its conjugate is the same as the number itself. And here I take this conjugate sign will then split up by this into a conjugate sign over each term. And then the conjugate sign over each term will split up into conjugate signs over each factor. That includes all the factors of R that are in that term. Okay, and also over the AN. But the AN are real, so they're the same as the conjugates of AN are just AN. Okay, so I'm taking the conjugate all the way inside each factor here. And the ANs are the same, so what I get is AN R conjugate to the N plus AN minus 1 R conjugate to the N minus 1, etc. The last two terms, by the way, are here it's A1 conjugate R conjugate, but that ends up being A1 R conjugate plus A0, since all the AI are real. Okay, and now what I have here then is the same polynomial as I started with, but R has been replaced by R conjugate. But we've seen that that's equal to 0. Okay, so simply substituting the conjugate into the equation, as long as the coefficients are real, it will give us another root. Okay, so that's why the roots come in complex conjugate pairs. Okay, so let's see another example. Okay, the quadratic polynomials are a good example. Good example to start with. So the degree 1 polynomials don't have, you can see they can't have complex roots. Right? So if you equate that to 0, you'll automatically get x is equal to minus b over a, only if a is not equal to 0. So there's only one root for such a polynomial. And so if it had a complex root, it would also have to have a complex conjugate root, and that would give you two different roots, and that's impossible for a degree 1 polynomial. Okay, so no complex roots here. For quadratic, degree 2, okay, so we'll have ax squared plus bx plus c. Okay, so then remember how you would do it using the quadratic equation. You would, if you were to solve for all the roots here, you would just equate this to 0, and then you would find using the quadratic equation that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. This expression here is called, under the square root, that expression is called the discriminant, capital D. So the discriminant is b squared minus 4ac. Okay, so we have three different cases. Case 1 is where d is greater than 0. Then the square root will be, in the end, will be non-zero, but it will be real, because what's inside is bigger than 0. So you'll get two different real roots. Two distinct real roots. Each of multiplicity 1. Okay. Furthermore, the polynomial will, okay, here a has to be non-zero. Okay, that is required also for the denominator not to be 0. So each root has multiplicity 1, and you can write, by the factor theorem, you can write the whole polynomial as a product of a. When you take a out, you get the polynomial of leading coefficient is 1, And then the two roots, you can write like, you can write the two roots and x in there so that this whole thing is equal to ax squared plus bx plus c. Okay, it's just a factor theorem. If you plug in x equals r1, that's a root, so this whole thing will vanish. That means there's a factor of this form, x minus r, 1. And the remaining factor must be the other distinct real root. Okay, the second case is where d is equal to 0. Capital D is equal to 0. So that's the first case. The second case is d is equal to 0. Then you have only one real root. It will be minus 2b over 2a. But it will be repeated. It will have multiplicity 2. Okay, so the final quadratic polynomial can be rewritten as a, and it will turn out to be x minus r. So the real root, call it r, and everything squared. X minus r quantity squared. Here they've called the real roots r1 and r2, by the way. And the third case, you can check these formulas, by the way. Multiply r, if you expand this and use that r1 as, say, the plus root and r2 is the minus root, then you'll get a lot of cancellation and you'll get this equation. Similarly, if you plug in this formula for the r and use the fact that the discriminant vanishes, then you'll be able to go from here to back to here. Finally, d less than 0 means you have an imaginary number coming up here, because this thing under the square root will be negative. And so when you take the square root, you'll get an imaginary number coming up. So the two roots are r1 is equal to minus b plus I, and then you have the square root of 4ac minus b squared. Okay, so this, you can take the minus sign out, and that takes an I out of it, and then what's left is a positive real number. And you can't take the square root of that. So these are the two roots. In this case. Okay, and again, you can write the whole quadratic expression as a times x minus r1, x plus r1. Oh, we can write them as r and complex conjugate of r. Okay. This number is a complex conjugate of this one. Oh, it should be negative. Okay, again, if I write this expression out, then what results in the end is this, using the formulas here. Okay. So these are roots of multiplicity 1. Two distinct roots, two distinct complex roots with non-zero imaginary part of multiplicity 1. Okay, so that covers all the cases for a quadratic polynomial. Okay, in practical cases, you don't have to use a quadratic equation. You can use completing the square. that's also where the quadratic equation comes from. So in some cases that makes it a little bit easier because you don't have to memorize the quadratic formula. Right, so it's a really good idea to memorize the quadratic formula, or at least understand and know the method by which you can get it, namely completing the square. All right, so let's see an example here. So my example was x squared plus 2x plus 2. So let that be equal to f of x. Okay. And the problem here is to, factor that in terms of factors which have complex roots in them. Factor it so that it's of this form. So a is equal to 1 here, so the two factors should be x minus r conjugate. All right, so f of x is equal to this. Now let's see how to do it by completing the square. Okay, so we have x squared plus 2x plus, and then I'll put this first in brackets, and then I'll put the 2 outside. The constant term goes outside. So in order to complete the square, I have to find something which will make this whole thing into a perfect square. So I have to divide this coefficient by 2, I get 1, square it, and I get 1. So I have to add a 1 in here and then subtract the 1 outside. Now inside I get x plus 1 quantity squared. And outside I get plus 1. All right, so now I can think of this as it's the sum of two squares, namely x plus 1 squared plus 1 squared. And so as I did before, I could split that. Remember I split x squared plus 1 up into x minus I, x plus I. So here I could do the same, just treat this as x, the x that I had here. So here I get x plus 1 minus I, x plus 1 plus I. And I can check this gives me back the same quantity by multiplying this out. Okay. Another way of doing this is by using the quadratic formula. So actually finding the roots and then writing, the roots will be of this form, r and r conjugate, and simply plugging them in this form. A will be 1. Okay, so I use the quadratic formula. Okay, so x then is equal to, so I solve for this equals to 0. And then I get x is equal to minus 2 plus or minus square root of, b squared is 4 minus 4ac. 4 times 1 times 2 is minus 8. Divided by 2 times 1, which is 2. Okay, so here I get minus 2 plus or minus. Now I get the square root of minus 4 over 2. So I get minus 2 plus or minus. This whole thing is 2i. So I can take the 4 out first, and I get 2 outside, and then square root of minus 1, which is I. Okay, and divide by 2, and so in the end I get minus 1 plus or minus I. Okay, so this is r. Let's say r is the positive root, positive I. And r conjugate then is going to be minus 1 minus I. So to factor that, I just write it as x minus r conjugate. Since if plugging in the value for x, if that gives me 0, then I know that value is a root. And I also know that x minus r is a factor of the polynomial by the factor theorem. Okay, so x minus r is plus 1 minus I. X minus r conjugate is x plus 1 plus I. And that's the same as before. So that's the alternative way of factorizing this using by completing the square or using the quadratic formula. Okay, so let's do some try it examples. This is section 5.5. Here I'm going to this is number 1. Okay, so the polynomial is 2x to the 5th minus 3x to the 4th minus 9x cubed plus 8x squared and plus 2. And we're supposed to use the remainder theorem to evaluate f of x at x equals minus 3. Okay, so remember how we do that? We simply use synthetic division. And that's the most straightforward approach. Avoids lots of complicated calculations. Or we could plug in the numbers. So just to illustrate how this could be made a bit easier by using synthetic division, I'll do it 2 ways again. By plugging in the number and then also by simply using synthetic division. Okay, you could, in a test, what you could do is use synthetic division. That's the quickest way to get the answer. And then to check the answer, you can do it the longer way, if you have time. Right? It's always good to also check your answer directly in case you made mistakes along the way there. But if you have extra time, you can always do it a completely different way. And that way, if you do get the same answer, then that makes you a little bit even more sure that you got the right answer in the first place. Okay, so write down the coefficients of this polynomial. 2 minus 3 minus 9. 8, and then I have to skip one here at the end, the x term, that gives me 0, and then 2. And then I put in minus 3, and go ahead and evaluate. So this, I write down the same coefficient 2. 2 times minus 3 is minus 6, minus 3 is minus 9. Minus 3 times minus 9 plus 27, minus 9 is 18. Minus 3 times 18 is minus 54, plus 8 is minus 46. Minus 3 times minus 46 is 138. Plus 0 is 138. And finally, minus 3 times 138 is minus 404. No, sorry, 3 times 8, 24. Minus 412. Sorry, minus 414. can always do this as a separate calculation on somewhere else on the page. 24, carry the 2, 3 times 39, 40, I get 41, yeah. And then plus 2 gives me minus 412. Okay, so the numbers you can do in your head mostly, except maybe here, and then you need a little bit extra work. But it's not too hard to get that. Now if you check it directly, then the calculation becomes a little bit more complicated. So it shows the utility of this synthetic division method. And you can check that what you get here is, I'll just write it out, minus 2 to the times minus 3 to the power 5, minus 3 times minus 3 to the power 4, minus 9 times minus 3 to the power 3, plus 8 times minus 3 to the power 2 plus 2. So I just plug in minus 3 into all these terms. Okay. So minus 3 to the power 5, that's the overall thing will be negative. That's minus 2 times 243. It's 81 times 3. This is 81 times 3 again, so that's going to be, again, minus 243. This will be also plus 243, so I'll get cancellation between these as it turns out. This will be 9 times 8 is 72 plus 2. Okay, so anyway, this may or may not be easier for you than this, but we get minus 486 plus 74, and so we do get minus 412. Okay, so either way should give you the same answer, and it's good to check, as I say. Then you can be ultra sure that you're getting the correct answer. And finally, the try number 2. That's what I wanted to do. Okay, I would urge you to do all these try-it problems. Try them out, because the answers are in the back of the book. There's a special answer section for them. All the answers for them are given. Try them out without looking at the answer first. Try as much as you can before finding out what the answer should be. And if you have trouble, look at the actual worked out problem. They're actually always work out a problem first and then give you try-it problems. So it's a good way to learn in sequence what's going on. And remember, math builds upon itself. So if you miss one of them out, then it might be harder to learn subsequent things. So the try it number 2, again, is in section 5.5. We're asked to use the factor theorem to find the zeros of f of x is equal to x cubed plus 4x squared minus 4x plus minus 16. Given that x minus 2 is a factor of the polynomial. Okay, how would we know that x minus 2 is a factor of the polynomial? Well, maybe one way of doing that is you can do some polynomial. You can do some checking of numbers to see if synthetic division will give you 0. And just to do that, just to verify that this is in fact indeed a factor, I take x 2 times 1, it gives me 2 plus 4 is 6. 2 times 6 is 12, minus 4 is 8. 2 times 8 is 16, plus 16, or minus 16 is 0. So indeed I get 0 as an evaluation. Okay, so synthetic division actually gives us the coefficients of the quotient polynomial. And then we need that to find the remaining factors. So number 1, it is a factor. Checks that it is a factor. Gives us a 0. Number 2, we get the coefficients of the quotient polynomial. So we can find the remaining factors. Okay, so once we get all the factors, okay, so what is the remaining factor? Q of x is, so f of x is equal to then x minus 2 times q of x, where q of x is equal to not x cubed, but 1 less. You go down here and it's always 1 less. So x squared plus 6x plus 8. Okay, and now this we can factor. We can recognize this is 2 times 4, which is, when you add the 2 and 4, you get 6. So you can immediately see it's x plus 2, x plus 4. Okay, and so you get the full factorization is x plus 2, x minus 2, and x plus 4. Okay, and so the roots are, or the zeros are, just wherever, you just take the negative of these terms here. So you get 2, minus 2, and minus 4. Or in the increasing order, minus 2, minus 4, minus 2, and 2. All right. Okay, and I think I pointed out, if you wanted to check, you can simply multiply this out and get the original, show that you get the original polynomial. Another way to do it, since I mentioned the grouping method before, you can also do this from scratch, from the starting point by checking to see if the grouping method works. And indeed it does. So you can factor this. So you group these together and you take out the common factor, it's x squared, and you get x plus 4 from that one. And you group these two and you take the common factor, it's minus 4. And what's left is x plus 4 again. So here grouping works and gives you the factorization x squared minus 4 and x plus 4. And here this x squared minus 4 splits up, it's a difference of squares, so it splits up into x plus 2 and x minus 2. So you get the same factorization, and from there you get the same roots. Okay, so that's all I wanted to do for this extra part 2. So next time I'd like to continue with finishing section 5.5 and trying to finish the rest of chapter 5 as well. And I'll continue to work on grading the other assignments and get them handed back. I'd like to give you a practice quiz for chapter 3 first. I'll give that to you as soon as I can, and you can work on that. That will be homework, but it will be a practice for the quiz, the first quiz we're going to have, which will be done using Maple. And then I'll give you the actual quiz. So it'll probably take about a week to get there. Okay? And you'll have practice on problems that you haven't been asked to do before as well, so like inverse problems and so on. Okay, so I'll just cover chapter 3 for now. I'll try it out like that, and anyway, for me it's a learning process getting all the getting everything together in the right order here. Okay, so thanks for listening to the lecture, and take care. Rudolphus, have a good night, or a good day if you're watching this in the day. All right, see you and bye.